Let's dive right into this explainer. We're going to take what looks like a dry, dusty operational rulebook and turn it into a masterclass on the unforgiving physics of heavy industry. You know, when you step onto a drilling rig, you're walking into a world where massive forces like gravity, pressure, and geometry are just constantly in play. Today, we're unpacking the blood-written rules that actually keep people alive out there.
I want to set the stakes right out of the gate. On a rig, safety is absolutely not about bureaucratic caution or ticking boxes on a form. It is dictated entirely by unrelenting math and gravity. And as this quote perfectly points out, the biggest danger, it usually doesn't come from those massive half-a-million-pound showcase lifts. No, it's the everyday, routine material handling that catches people completely off guard.
So here's our roadmap for today. 1. The danger of routine lifts. 2. Handling pipe and geometry traps. 3. The invisible physics of heavy gas. 4. Mastering pressure and fluids. And 5. Design, data, and redundancy.
All right, let's jump straight into Section 1, the danger of routine lifts.
So here's a quick test for you. Rigs use a separate lifting path called a cat line. It's basically a small secondary crane acting like a scaffold jib. This exists so that routine work never competes with the well, and drilling never has to stop. But if you're just lifting, say, a toolbox or some spare parts, why is it absolutely mandatory to use a tagline and bury her off the drop zone?
Well, it's because a suspended load is going to spin. Once it's up in the air and spinning, there's no way to safely control it without getting right underneath it. A tagline lets you control that deadly rotation from outside the drop zone. Remember that opening quote? Routine lifts are what actually hurt people. If a lift requires somebody to put their hands on it while it's in the air, the whole plan is just wrong.
This actually perfectly illustrates the wider physics of hoisting. Think about the massive derrick structure. The crown block at the very top carries way more than just the hook load. You literally have to add the tension from both the fast line and the dead line. Plus, when you reeve the hoisting system, adding more lines gets you more lifting capacity, sure, but it eats into your speed. Stringing is always a job-by-job decision, trading shear capacity for trip speed.
Moving on to Section 2, handling pipe, geometry traps.
Let's talk about pipe. A standard 30-foot joint of drill pipe weighs right around 600 pounds. When you lift one end of that joint, it stops being a pipe and becomes a sweeping pendulum. Standing at the end of it puts you directly in a lethal, knee-height arc. This is exactly why you always stand at the side of the pipe on the catwalk or the pipe ramp, never at the end. Constraint and positioning beat raw capability every time.
Now in this environment, positive geometry always beats friction. Think about the Kelly. That's the heavy pipe that rotates the drill string. It's square or hexagonal, right? Not perfectly round. Those flat faces transmit torque mechanically. They don't rely on something as flimsy as friction. And when you're inspecting these tools for metal fatigue, you don't check the middle. You inspect exactly where the geometry changes, like the bail eyes or the Kelly's flat to round transitions. That is where stress concentrates and cracks actually form.
So, a huge part of geometry is knowing your exact starting point. On a rig, this is the depth datum, usually the Kelly bushing. Every single depth on that well is measured from this one point. Why? Because a depth without a stated reference point simply isn't data. Get your datum wrong and you might fire perforations 25 feet in the wrong zone. You could literally ruin an entire well by connecting to water instead of oil. It's that critical.
Okay, let's head into Section 3, invisible physics, heavy gas. See this number, 1.19? That is the specific gravity of hydrogen sulfide, or H2S. Since it's greater than 1, it means this incredibly toxic gas is heavier than air. And because it's heavier than air, it sinks. It literally flows downhill like water, searching for the lowest unventilated spot on the rig.
So think about this terrifying scenario for a second. You need to work in the cellar, which is the concrete pit directly under the rig floor. Every single gas monitor up on the breezy rig floor is reading a perfect 0. So is it safe to climb down that ladder?
Absolutely not. Just like water flooding a basement, that heavy gas sinks straight down into the cellar, while the air 30 feet above stays totally clean. Clear readings on the rig floor tell you absolutely nothing about the pit below. That's why the cellar is a strictly governed, confined space. You have to test the atmosphere in the exact space you're entering at the depth you're entering it immediately before you go in.
Let's keep moving. Section 4, mastering pressure and fluids.
Let's check your instincts again. You're pumping cement down a casing.
You hit your pre-calculated displacement volume. That's the exact amount of fluid needed to push the plug to the bottom. But you don't see that satisfying pressure spike on your gauge to confirm the plug landed. So do you chase the bump? Do you pump just a little bit extra?
No, you stop immediately. You have to trust the calculation over that gut feeling that one more barrel will fix things. If you keep pumping, you risk over-displacing and forcing all that crucial cement out past the bottom of the shoe. That leaves the bottom of your well completely uncemented, turning a precision operation into a ruined well with a wet shoe. Never pump extra chasing a bump.
Now, when you're executing a squeeze job to patch a leak, you're basically forcing cement into a channel. The golden rule here? Your squeeze pressure absolutely must stay below the formation's fracture pressure. It's kind of like using a caulking gun. You're just trying to fill an existing gap. If you push too hard, you fracture the rock, blowing a brand new hole open and losing your cement straight into the formation.
And this plays directly into well control. When you're circulating a kick out of a well, the absolute rule is to hold your drill pipe pressure constant. Why? Because holding the drill pipe pressure constant holds the bottom hole pressure constant. You do this by working the choke. Closing the choke raises the back pressure, and that back pressure is exactly what holds the formation fluids back. So, seeing a rising casing pressure during a kill is actually completely expected.
Finally, let's wrap up with Section 5, Design, Data, and Redundancy.
Good design totally depends on accurate data, which means you really need to understand your tools. When making a connection, pneumatic spinners will spin the pipe fast to make up the threads, but they can't apply precise tension. A stalled spinner just means it ran out of air power. It is definitely not a torque reading. Spinners make up threads, but only those massive steel tongs can set the true calculated torque you need.
Also, we never ever work behind a single barrier. That's why a wellhead tree has two master valves. The lower master valve is deliberately left unused during normal operations. Why do we do that? So that if the upper valve fails, the lower one is pristine and can be totally trusted. But here's the catch. You have to cycle all these valves on a strict schedule. A stationary valve that never moves is a valve that won't close when you're in a real crisis.
And that brings us to one of my absolute favorite engineering concepts, pre-planned failure. Good rig design chooses, in advance, exactly which part is going to break. We intentionally design cheap, sacrificial parts like a bit sub, a saver sub, wear bushings, brake blocks, or bumper blocks. They are literally built to be destroyed. They take the beating so that your primary systems don't suffer a lethal, catastrophic failure.
So I'll leave you with this thought to chew on as we wrap up this explainer. True engineering isn't about the arrogant assumption that you can prevent failure entirely. It is about gracefully designing the failure. If the best engineers out there are planning exactly where a massive system will break to protect the whole thing, are you designing your own safety margins, or are you just crossing your fingers and hoping for the best? Think about it.